Hey everyone, welcome to A5 Dot Point. This one's about using nutritional data to determine the suitability of animal feeds in terms of energy and protein requirements for particular stages of production for one monogastric and one ruminant. So what we need to do here is we need to look at energy and protein for two animals, one a monogastric and one a ruminant. So let's have a look at this first table. This is divided up into energy first here. We're looking at energy and then we'll look at protein. So this is an example of some information that's out of the textbook. We can see these different feed types here, how much in megajoules per kilo they provide in their feed. And then over here we have some different animals and their megajoule requirements per day. So we know from our diets that we can measure our feed in calories or in kilojoules, and megajoules is another way of measuring that. So here we have wheat grain, for example, and oat grain, which give about 13 megajoules per kilogram of feed. Looking at hay here, different types of hay, that drops down. The amount of energy per kilogram is a bit less. If we look over here to these different animals, so a 40 kilo sheep just for maintenance and no production requires around about 7 megajoules. A pregnant ewe, a little bit extra, about 8 or so, 9. And then we have a look at a lactating ewe, so not pregnant anymore but producing milk, requires about 17. So basically double the amount of energy required for an animal that's not pregnant but producing milk. Then here we have a 200 kilogram beef steer, about 27 megajoules per day. And then lastly, a 450 kilogram beef cattle steer, just for maintenance, requires about 49 megajoules. So if we have a look at this next question, choose one of the animals you graphed on the previous page, outline how you might meet their energy requirements for a full day. If we have a look at a beef steer here and it requires 49 megajoules per day, it's 450 kilograms. There's a couple of things we could do. Firstly, if we fed them 4 kilograms of wheat grain, 4 times 13 would get us up to the energy that they require. But we know that you can't just feed an animal, a ruminant, 100% grain. So we need to kind of supplement that with some hay. So if we fed it, say, 3 kilograms of wheat grain and then maybe a kilo and a half of lucerne hay, that would get us up to 51 megajoules per day, which is enough. Remember, this is just maintenance energy, so you can't feed it less than what it requires. If it requires 49, you need to give it 49 or more, not 48 or less. So it would end up having 51 with that combination, which is enough. And then that would give us about 75% grain and 25% roughage, which would prevent the animal from getting bloat. If we move on and look at protein, I've graphed here different feed types and the percentage. This is not per kilo, this is just a percentage. So you can see here, for example, linseed meal is about 31% protein. And then animals' requirements in their feed. So a very young chicken, a monogastric, requires 22% protein. A laying hen can do with a lot less, about at 15%, and then it drops off. A non-laying hen only needs 7. Then we move on to the ruminants. So we've got sheep and cows. A lean sheep only requires 6. The one you're trying to fatten up and put more muscle on requires more protein at 10% in their feed. A lactating cow requires 15 because it's producing milk, and milk is high in protein, whereas a pregnant cow that is not producing milk doesn't require as much protein as one that is not pregnant but producing milk. So let's have a look at the first question here. Choose a monogastric animal you've graphed on the previous page and outline how you might meet its protein requirements. So a monogastric, an example is a chicken. This is a very young chicken in the first couple of weeks of its life. It needs at least 22% protein and in its feed because it's growing and putting on a lot of muscle. Of the feeds listed here, there's only one feed that would meet that. So linseed meal, if we were going to feed it one of these or out of these feeds here, we would have to give it some amount of linseed meal because it's the only one that goes above 22. But what we could do is we could mix it with something else like wheat grain, which is lower, until we got to the correct amount, which gave it 22% protein in its total feed. Any protein that we give it above this is wasted. It's not needed by the animal. It's not used. And it's basically, because protein is very expensive, it's going to be a waste of money. If we have a look down here at a ruminant, so we choose a ruminant animal you've graphed and outline how you might meet its protein requirements. So if we have a look here, we've got 4 ruminant animals. sheep and cows, and I've chosen a lactating cow, which is this orange one here, which means it's producing milk. It needs 15% protein in its feed, and so there's only one feed that has more than 15%, and that's linseed again, which has 31. So we'll need to feed it some linseed meal, but we could also mix that with something like lucerne, so it's got roughage in its diet, and we can make sure that the proportions are correct so that it gets the 15% of protein that it requires in its feed. If we have a look down here at this next question, explain why this ration here, and this is meant to talk about the finishing diet, and it's 75% grain, and the rest is roughage. Explain why this ration would not be suitable for an animal entering a feedlot on day 1. Suggest possible changes to the ration. So, the finishing ration above would not be suitable because it's too high in grain and it risks the animal getting bloat. We know that. This is an animal entering a feedlot on day 1. Using a lower grain and higher fiber roughage diet initially would reduce the chance of bloat when entering a feedlot, and an example is the starter ration, which is given there for you to give as an example. Moving on to a monogastric. Here we have a broiler, which is a meat chicken. They only live for 7 weeks before they're slaughtered, and here's some information about their diet. We already know about feed conversion efficiency or feed conversion ratio, FCE or FCR, and we know that monogastrics are quite efficient. They only take 1.9 kilos roughly of food for every kilo of weight gain. Now these chickens are fed 3 different diets throughout their 7-week life. The first one being a starter diet for the first 2 weeks. The next one being a grower diet for the middle 3 weeks, weeks 3 to 5. The last one being a finisher diet for the last 2 weeks before they're slaughtered. So you'll notice in here the components in their feeds, and they change. And this is basically the ones that change, and these are the ones that stay the same here. And here, let's have a look at the differences. So protein is very high at the beginning when they're putting on a lot of muscle very quickly, and then their muscle development slows down significantly. And so the protein in their feed drops off. If you're feeding them high protein all the way through when they're not using it, it's a waste of money. So farmers don't do that. Fat increases because, as we know, the tissue that animals put down, first they put down bone, then they put down muscle, and then they put down fat lastly. So as the animal ages, it's starting to put down more fat, and so its fat in its diet increases. Salt changes. We know that salt increases or stimulates appetite and also prevents urinary infections. So as the animal's getting older, it decreases the amount of food I guess it needs to be stimulated to eat, and that is one reason there. So animals first put on bone, and these are the reasons why it changes. They put on bone, then muscle, then fat. Protein decreases because it's expensive and they don't use it as much, and fat increases as it's deposited towards maturity. So urea is one of the things that stays the same. There's none of it in there. It's listed on the label, but it's none in there. And part of the reason is because it's not used by monogastrics, only ruminants. All right, on to past HSC questions. This is a question from a few years ago, question 20. Question 20 is always quite hard. And this one is hard because it requires you to synthesize information between 3 tables here. So there's this one, and this one. The first one shows the feed requirements of sheep, so how much they need of both energy and protein. This one shows how much is contained in the feed that they're asking if it's okay. And this third table shows how much each animal listed here will eat each day. So 5 kilos, 4 kilos, 5 kilos, 4 kilos. So let's have a look. We've got the shaded bars here represent energy, and the white ones represent protein. And I've written this down here so I can go along and tick which one is going to be adequate for energy, which one's going to be adequate for protein. If it's not adequate, I've put a cross in there, which rules that feed out for an animal. So this is requirements here. So let's have a look here. This supplementary feed, which we're talking about, and it says use the information above for which pair of sheep types is the supplementary feed suitable. So let's have a look. The supplementary feed information is here. It contains 10.5 megajoules per kilogram of energy. If they eat 5 kilos, that leads to 52.5 megajoules provided to the animal that day. If they eat 4, it's going to give them 42 megajoules provided, and then 52.5 again and 42. So let's have a look if the energy is adequate. So first of all, this side, the feedlot lamb requires 50 megajoules per day, and it's going to get 52 from the feed. So that's a tick. It will be sufficient. If we have a look here at the pregnant ewe, it requires 40 megajoules per day, and it's going to get 42 from the feed. So that's a tick as well. The lactating ewe requires 60 megajoules a day, and it's only going to get 52.5 from the feed. So that's a cross that this feed is not suitable for energy for a lactating ewe. The weaner requires 40 megajoules per day, and it's going to get 42, so that's a tick. That will be sufficient. So already we know that the lactating ewe, this feed will not be suitable for. Moving on to protein. Protein, we don't need to worry about this table because it's a percentage. It's not an amount, it's a percentage. So it's 15% of this feed is protein. We have to use this side for protein. So we can see here that the feedlot lamb requires 15%. So that's a tick. It will have enough protein. The pregnant ewe only requires 12% protein. Now remember, we can provide extra, but we can't provide less. So it's being provided extra in the feed. It's being provided 15% when it only needs 12. And we have a tick there for protein that will be adequate. Lactating ewe requires a little bit under 15, and it's going to provide 15. So a tick, it will provide enough protein, but remember, not enough energy for the lactating ewe. And lastly, the weaner requires, it's a close one, but it's actually probably 16 here, and it's only going to provide 15, and that's not enough, even though it might sound close. So that is a cross. So the two that will not provide enough energy and protein for this feed is lactating ewe and weaner, meaning that this food will be adequate for feedlot lamb and pregnant ewe. So the answer is C, feedlot lamb and pregnant ewe. If we move on, question 4, the graph shows the recommended metabolizable energy levels measured in megajoules per kilogram needed for a breeding ewe during production. So this is joining here, or mating. This is lambing when it's giving birth, and this is weaning when the lamb is no longer drinking the mother's milk and is starting to eat solid food. So milk production will drop off then. The question is, first one, account for the increasing metabolizable energy levels leading up to lambing. So at this point, down here we have joining. When the animal's mating, there's only a few cells that when conceptions happen, there's only a couple of cells growing in the growing embryo, so not a lot of extra energy is needed. But as the animal, the fetus, the lamb starts to grow in size before birth, it's becoming bigger and heavier, and that's what I've written here. The lamb is getting larger, requiring more energy to keep it developing, leading up to birth. Also somewhat related is when the mother is getting closer to birth, the mother is starting to produce milk. And as we know from earlier, milk is high in energy requirements. So the energy requirement for the ewe is going up because it needs to start producing milk and therefore has an energy increase requirement. Explain an effect on ewe fertility of increasing metabolizable energy levels prior to joining. So this is conception here. Before that, this is what we call flushing, when you're giving a ewe extra nutrients before mating. And the reason is because it increases the chance of conception, increases the rate of twinning, because the animal puts out, is more fertile, is more likely to put out more than one egg, which can lead to twinning in an animal. So basically here, increased metabolizable energy before joining or mating increases ovulation rates, therefore high fertility and more chance of multiple eggs and twinning.